Our first keynote speaker today is Prof Giorgio Metta, who is no stranger to A-Star, having served as advisor to A-Star's Robotics Horizontal Technology Coordinating Office since May 2022. Giorgio Metta is the scientific director of the IIT. He was one of the 3 Italian representatives at the 2018 G7 Forum on AI, and more recently, one of the authors of the Italian Strategic Agenda on AI. Prof. Metta coordinated the development of the iCub robot for more than a decade, making it the de facto reference platform for research in embodied AI. Presently, there are more than 40 robots reaching labs as far as Japan, China, Singapore, Germany, Spain, UK, and the US. In fact, one of our collab AI PIs has an iCub in his lab in this very building. So Prof. Metta's research activities are in the fields of biologically motivated and humanoid robotics, in particular, developing humanoid robots that can adapt and learn from experience. Prof. Metta, thank you for joining us today. The floor is yours.
Thank you. So, good morning, everyone. Thank you for the nice invitation. Very glad to have the opportunity to share some of my research, although albeit not directly my research, meaning that I don't have a research group since 3.5 years, being director of the IIT. Doesn't entail or doesn't leave any time for research, but I'm reporting research from a few of my collaborators, and in particular in 2 areas of human-robot interaction that I think are relevant for what we're discussing today. These 2 areas are interaction via non-physical contact and interaction via physical contact. So there are 2 groups developing different strains of research that I'm going to highlight in a moment. Well, first of all, a bit of inspiration. We started from this one, although this was a movie, as you can or may remember, one of the few movies where the robots were friendly, nice to people, working with us as they are in reality, rather than the usual, catastrophic scenarios or dystopic scenarios presented in the big blockbusters. Well, this was the inspiration. This was the project that actually many years ago allowed to design a human robot for carrying out our research. Cecilia was sitting here, was part of this project many years ago, and it was, I think, a great success in the sense that I think it's a bit uncommon for a standard research project to actually develop hardware and make sure the hardware survives the duration of the project. This is what happened, I must say, with a lot of support from the IIT that poured money to make sure we could replicate the robot, engineered properly, create a reasonable bill of material, and the construction process that allowed us to duplicate the robot, which is far from straightforward, considering that the robot is made of more than 5,000 parts, and you had to manage the complexity in that case. I like to compare this robot, nonetheless, to a Formula One car, not because it's particularly fast, but because it breaks as often as a Formula One car. So, it runs a Grand Prix, and then you have to replace the motor or the engine in that case. And here is the same. You run a couple of experiments, and then you have to replace tendons and or other components. Well, a couple of details on what was actually engineered into the robot hands for relatively sophisticated manipulation, although not very powerful or not powerful enough for real world manipulation. So small and lightweight objects, those are okay, but enough for studying the controllers that are needed for actually moving the robot. And then sensors, wanted to put as many sensors as possible. And actually what we did was to use or to put the usual cameras, microphones, but more importantly, tactile sensors. And I think this is one of the few robots that has been equipped with a full body tactile electronic skin. And eventually we made also the project entirely open source, which allowed to um, duplicate the robot to actually make sure other people could use the robot, both in hardware and software. So it's not only downloading the software or the simulator of the robot, but it's actually also um, having the ability to look at the drawings and all the electronics and the wiring diagrams that are useful in case you have to debug the robot. The next slide is a video that shows some of the capabilities of the robot, in particular the hands that I mentioned earlier. And this um, one of those easy experiments where the robot is reconstructing the object in 3D and actually planning a grasping motion and grasping the object. Not doesn't work always, so bear with me. The video, though, is representative enough of the behavior of the robot. Also, I mentioned the tactile sensors. This is an example of zero gravity, so gravity compensated robot movements, where if you can see kind of gentle touch still allows the robot to be moved around. And since I mentioned the open source, there are, I think we built serial number 51 the other day. Therefore, I mean, the story is continuing. There are still a few requests for a robot that is now more than 15 years old. So technology, unfortunately, is becoming very old. But still, we managed to do research on the platform. So one type of research, I mentioned human-robot collaboration without contact. And this is one, let's say, paradigmatic experiment that we carried out. And this was actually duplicated also or replicated here in Singapore, because we wanted also to test whether there are cross-cultural differences and so forth. But anyway, experiment is very simple. It's called Posner queuing. It's a standard psychology or experimental psychology method. And Posner originally used an arrow to actually queue a certain location. So you are sitting in front of the screen, you see an arrow, there's a stimulus appearing, a letter, and you had to press a button to identify the letter. And a letter can appear coherently with the arrow, so on the same side or opposite. This is called a valid queue. This is called an invalid queue. And since the arrow is a conspicuous symbol, what happens is that we tend to be faster in responding to this one rather than this one. Now, we wanted to test what happens if we use a robot instead of the arrow, a real 3D stimulus in this case. And this is what happens. We modify the experiment a little bit. What happens is that at the beginning, the robot may be looking at you or actually averting gaze, so looking down. And wanted to see whether this small modification actually influences the overall response of the person that is in the subjects that are interacting with the robot. So here you see the video of how the experiment goes. Results, this is one we see in the case of eye contact, there's a difference between valid and invalid, which means that indeed gazing changes something. In case of no eye contact, there's the effect is not there, so it disappears, which is a nice story. Unfortunately, it's not entirely correct in the following sense, that if we start manipulating the timing of the appearance of the stimulus with respect to the actual movement of the eyes of the robot, things change, as if the duration of, or this time allows for different processing by the brain. And in fact, this mutual gaze is only valid within a certain time or time distance or interval of time between the appearance of the stimulant and the actual response. So to cut a long story short, yeah, the social signal of mutual gaze actually influences behavior, and this proven by the experiment. But and this is also I mean, this is treated as a social signal, so it's engaging and alerting. But the timing is very important. So if we're building a robot that needs to interact with us, maybe you should take into consideration how long it takes, or when you generate that very movement, when the robot looks at you. And therefore, it's very complicated. So in a complex human-robot interaction, we may require to control very precisely the timing, very precisely within a few hundred milliseconds, but still very precisely with respect to the unfolding of the overall action. Let's see a slightly different experiment, because this is, I think, interesting also in general, with respect to the claim that we may want to have social interfaces when interacting with human robots, or in general with robots, also in, let's say, industry setting. Here, the experiment is a little video game, participant, robot. Again, the robot may look at you, gaze at you. And as you can imagine, it's very easy to write a piece of software these days that uses robot cameras to find your eyes and just stare at your eyes, or look at your eyes. Anyway, here it's a little game. So you're controlling a car. The robot is controlling another car, and you can go straight or deviate. If you deviate, you avoid crashing for sure. If you don't deviate, you may crash. Depending on what you do, you have a different set of points. Of course, I mean, if you go straight and the robot deviates, you win. So you get maximum points. And if you rather keep deviating, of course, you don't crash, but you get minimal number of points, and the robot wins. So you like to actually maximize your score. And let me quickly show you how it works in reality, if it does. Okay, difficult to skip on the video. Anyway, you can imagine how it works. The video game is shown on a screen, sitting there on the table. The robot, as earlier, can look at the eyes, into the eyes of the participant, and you play the game for long enough. Let me show the results also in this case. And here what we have is the following. Mutual gaze kind of shows you longer response time. What it means is that basically, irrespective of whether the robot is more looking at you or less looking at you, so there are different characters, I mean, different personalities in the robot, and we're playing with also with this parameter, but doesn't change much. The important thing is that the robot looking at you slows you down. So, and this is intuitively is correct, because it's causing, there's some additional burden and you have to process an additional signal. So this is kind of interesting, because you may remember robots that had the nice interface. I mean, even industrial manipulators, where they put nice interfaces trying to, attract your attention on doing things. Well, this may distract you. In fact, you may be less efficient if you have a robot kind of looking at you. Maybe it's better not to do that. I don't know. I mean, still to be further tested. We replicated the experiments also checking through EEG. So our participants were not only playing nicely the video game, they were also being recorded from EEG. And we also checked, we got the same results. We also checked what strategy is being implicitly being used by the participants. So participants don't know what is the optimal strategy, but we tried to check whether, or we wanted to check whether they're using, in fact, an optimal strategy. The optimal strategy is called win, stay, lose, shift. So if you win, you keep doing that. If you lose, you change behavior. So if you lose because you were going straight, you deviate at the next trial. This